have reached the most important video of the series. Up until now, we were talking about the Goto's algorithm. So now we have to answer the question, what makes the profile aligner different? Unlike the regular alignment algorithms, which take the sequence as its only input, the profile aligner also accounts for the functional importance of individual bases. But how do we define the functional importance of a base? Over here we have a figure of an enhancer from a Drosophila species. And we see the letters that are enlarged in size, and those letters indicate the motif. We briefly talked about the motifs in the introductory videos, but as a reminder, motifs are the segments where the transcription factors bind. On y-axis, we have numerical values of individual base, indicating the contribution scores. High contribution score means that this base is important for transcription factor binding. And we see that these bases in the motif, they have high contribution scores because by definition, motif is a region where the transcription factor binds. And that's how the profile aligner defines the functional importance. To reiterate, bases that contribute to binding of a specific transcription factor are important and therefore more conserved than the neutral bases. Now, let's say we are looking at the same enhancer from two different but closely related species. And we are looking at here. So these lines on top, they represent the binding profiles, and the peaks are the motifs. And we want to answer the question, does integrating the functional importance data, in other words, the binding profiles, help the alignment? We know that motifs are less likely to be mutated throughout evolution, and in theory, this information can help us anchor the alignment by attempting to align the peaks. So, here, the peaks are differently spaced, as you can see, but what if the more accurate alignment is something like this, the one where the motifs are conserved? The profile aligner approaches this question by assigning different weights to sequence-based versus function-based alignments. And over here we have this infographic that helps us build intuition for how these weights work. We control the weights using the parameter called alpha, which ranges between 0 and 1. And when alpha approaches to 1, it means that we put higher weight on the sequence-based alignment. Whereas when alpha approaches to 0, we are trying to align primarily based on the function or the transcription factor binding profiles. So with this intuition, we can move to the math behind this implementation. And we have these three sets of equations. The first equation defines how we compute the sequence loss. We see that and we'll go through an example to exactly understand how the math works. The second equation computes the difference between the profile, or more accurately, contribution scores. And the third equation puts the equations 1 and 2 together and computes the weighted sum. To better understand these equations, let's take a look at an example. So, we iterate through individual aligned bases in order to compute the loss for this pair. So let's start from this A and A basis. We see that the sequences are the same, therefore we don't penalize the alignment, and the penalty for the sequence-based alignment would be 0. As for the profile-based alignment, we want to find the difference between the two. So this would be 0.4 minus 0.2, which is 0.2. Then we want to compute a weighted sum of these two, which would be our loss. And this would be alpha times 0 plus 1 minus alpha times 0.2. So this is for the first pair. Now let's take a look at this one. We see that the sequences don't match, so our sequence penalty will be 1. As for the profile, it would be 0.1 minus 0, which is 0.1. And then we'll have the loss, which would be alpha times 1 plus 1 minus alpha times 0.1. And depending on the alpha values, we may get the loss to be lower either for this one or for this one. So if alpha value is higher, meaning we prefer the sequence-based alignment, then the loss or penalty will be higher for this one. Whereas if we prioritize the function-based alignment, it's possible that the loss is higher for the first pair. And this is getting cluttered, but we are also approaching the end of this video. So to summarize, and I think this serves as a good summary graphic, the main idea behind the profile aligner is that we are integrating a new input on top of the regular sequence input, and this input represents the functional importance of individual base, and we integrate them by assigning different weights to those. And we want to identify what parameter values, or in this case, what alpha values lead to better alignment. And this concludes our video series. Thank you for watching.